If you want to say something that'll reliably start an argument around the dinner table, try this. There is no truth in science. There are only the best explanations of the evidence so far. But everything, and I mean everything, is provisional. Which, in a world where we all crave certainty and firmly held beliefs, sounds pretty bleak, but it's actually science's superpower. It's the one major human institution that builds in the inevitability of being wrong. Now, I've got to be really careful saying things like there's no truth in science, because people immediately start thinking that you're going to sell them crystal healing or UFO conspiracy theories or a podcast. Science absolutely cares about what's true, but it cannot hand you platinum-plated certainty. But it can hand you a model, an idea, usually with some maths attached, that can make predictions. And if that prediction matches observable evidence, then the model survives. And if not, you tweak it or throw it out. I'll illustrate this point using one of the least controversial topics imaginable: how the planets move. Because for about 2,000 years, it turns out that our best ideas of the solar system were wrong, but in increasingly sophisticated ways, and it's how science works. We start with Claudius Ptolemy, a 2nd century mathematician, astronomer and geographer working in the Egyptian city of Alexandria. One of his biggest achievements, published in his scientific treatise The Almagest, was turning the geocentric universe into a predicting machine. Now, the basic picture looked like this. Earth is in the middle, the planets and the sun orbit in circles, and when the sky doesn't quite match predictions, we add more circles called epicycles, and some other fudges to keep the predictions in line with what we see in the sky. And you know, it's really easy to laugh now at geocentrism with 2,000 years of hindsight, but it does predict some of the things that we see in everyday life when we look up. It predicts the rise and fall of the sun, it predicts the motions of the planets across the sky, kind of, and it predicts the stars wheeling overhead during the night. So geocentrism wasn't wrong in the everyday sense of the word, but frustratingly for early astronomers, it didn't predict everything they saw in the sky with perfect accuracy. And the most notorious and frustrating mismatch between model and observation was Mars and its retrograde motion. You see, night after night, Mars drifts against the background stars just like you'd expect. But then for a few weeks it slows down, and then it stops, and then it moves backwards, tracing a little loop-the-loop before carrying on as if nothing happened. And geocentrism cannot explain that in a neat and satisfying way. You can make it cope, but only by bolting on extra machinery, circles on circles on circles, until the whole thing kind of works. And it feels a little convoluted, it feels a bit over-engineered, more like we're trying to make the solar system work how we want it to work than how it does work. Enter Nicolaus Copernicus, not a full-time astronomer, but a church administrator, trained broadly in law and medicine, doing astronomy as a serious side hustle that would eventually overturn our views of the cosmos. Copernicus proposed a model in the 16th century that seems dead obvious now, but at the time was radical. Put the sun in the middle. Thus, Copernican heliocentrism was born. Not only was this a completely heretical departure from the Earth-centric view of the universe, what a rebel, but it was a much closer approximation of reality. It explained all of the things that geocentrism explains, and Mars's retrograde motion. It turned that weird phenomena into a perspective effect. Earth undertakes Mars on the inside orbital lane, and when it does, Mars appears to go backwards from our vantage point. It's elegantly simple and solves the problem beautifully. But Copernicus also carried some cultural baggage that undermined the whole thing. He was addicted to circles. He just loved them because circles were perfect, and so it made sense that the planets would orbit the sun in perfect circles, because why wouldn't the heavens be perfect and angelic and flawless? The problem is, when you put the planets on perfectly circular orbits, you don't predict their positions with perfect accuracy. Model and observation diverges. In fact, it's not that much better at predicting their positions than geocentrism. But that's okay, because science is not a history of quick wins. It's a history of many centuries of incremental improvements, one person handing ideas to the next. And the next baton is carried by a man who thought you could understand the universe if you just measure it hard enough. Tycho Brahe was a 16th century Danish nobleman with two great advantages: money and conviction. Does that remind you of anyone? Tycho decided, quite sensibly, that if you want to understand the heavens, you should start by measuring them properly, night after night, with care and precision. And the Danish king indulged him, and so Tycho ended up with the island of Hven, where he built Uraniborg, Part observatory, part palace, with massive castle vibes. Imagine a modern research institution with more money, more stone masonry, and less HR, which actually sounds pretty good. He made all of his measurements before the telescope, by the way, and so had to use mechanical angle measuring instruments, such as quadrants and sextants, bolted down and painstakingly aligned. And it worked! Tycho measured the positions of the planets so well that his data became the ground that astronomy stood on for the next couple of centuries. Now, there is a small and important aside here. We need to talk about that nose. As a young man, Tycho got into an argument with someone and settled it with a sword duel, like you do. He lost part of his bridge in the process and so had to spend the rest of his life wearing a metal prosthetic. He also had a pet elk that lived with him in his castle, but unfortunately the elk died after drinking too much beer and falling down the stairs. Poor thing. So back to the planets. Based on his data, Tycho came up with his own model of the solar system, which was kind of a hybrid between geocentrism and Copernican heliocentrism, called the Tychonic system. In it, Earth stays put, the sun goes around the Earth, and all of the other planets go around the sun. Now, the Tychonic system sounds like an elaborate attempt to keep everybody happy, which, in a sense, it was, but there's a serious point. With the evidence available at the time, it could match a lot of the same planetary behaviour people cared about, including the retrograde motion of Mars. What it didn't do was magically solve the accuracy problem, because it relied on the same assumption that Copernicus just wouldn't let go of. Perfect, circular, uniform orbits. Now, by this point, lots of people were pondering what the solar system ought to look like, but no one could argue with what Tycho had actually seen with his sextants and his quadrants. And then into this world walked Johannes Kepler, intense, perpetually short of money, and absolutely brilliant. Kepler really tried to make the circles of Copernicus work, but they just wouldn't, especially for Mars. Where you would predict Mars to be in the sky just didn't match where it was in reality. And the discrepancy was small, just a couple of fractions of a degree. But Kepler refused to wave that discrepancy away because Tycho's data were just so damn good. So he did the one thing that the data were demanding. He let go of circles. And instead of circles, Kepler put the planets on elliptical orbits, with the sun sitting at one of the foci. That single change sounds like a really fussy bit of geometry, but it turned out to be the key that made the whole solar system behave. And from there, Kepler distilled 3 rules that today we remember as Kepler's laws of planetary motion. Here they are. Number 1. Each planet moves in an ellipse, with the sun at one foci. Not a circle, an ellipse, with the sun just off centre. Number 2. A line drawn from the sun to the planet sweeps out equal areas in equal times. What this means in practice is that the planets don't move at a constant speed. They speed up close to the sun and slow down further away in a very predictable way. And number 3, the time a planet takes to go around the sun is linked to the size of its orbit by a precise mathematical relationship. Bigger orbit, longer year, in a way that you can calculate precisely. These 3 laws are a distillation of Tycho's measurements, boiled down and synthesized until only the pattern is left. Kepler published them in 1609 and 1619. They worked far better than geocentrism and Copernican heliocentrism because they predicted everything that had been before, and they better predicted the positions of the planets. Now, by this point, Kepler had described beautifully what the planets do, but he couldn't explain why they did it. Why ellipses? Why the weird equal area in equal time things? And why the relationship between distance and orbital period? And so astronomy was sitting on a set of rules that worked, and they were just waiting for someone to come along and explain why. And that someone, of course, was Isaac Newton. Newton was not, by all accounts, an easy guy to work with. He was private, touchy about criticism, and capable of holding a grudge with the sort of long-term commitment most of us reserve only for mortgage repayments. None of which stopped him publishing Principia in 1687, his masterpiece, where classical mechanics really got going. In the Principia, Newton wrote down his 3 laws of motion, which you might remember from high school, and then he just casually added in his law of universal gravitation, which applies to everything, everywhere. And once you've got Newton's laws, Kepler's laws just fall right out of them. They stop looking like 3 clever observations and look like the inevitable paperwork. You see, planets are always trying to fly off in straight lines, but the sun's gravity bends their paths. The result is an orbit, and for this particular kind of gravitational rule, the one that Newton derived, the maths naturally produces the shapes that Kepler found. ellipses for planets that are bound to the sun. And this is a moment just to pause and really give Newton his due, because his model doesn't just kind of work. It works so well that we built the modern world on it. It gets satellites into orbit and keeps them there. It lets astronomers plan rendezvous in space, two objects hurtling around the Earth at several kilometres per second, and still arrange for them to meet with delicate precision. It got people to the moon, and then returned them safely back home. It guides rovers to Mars, and put Cassini in a neat orbit around Saturn. It flung the Voyager probes to the gas giants of the outer solar system, and it sent New Horizons to Pluto. Newtonian mechanics can send a spacecraft billions of miles across space and have it arrive at just the right place, at just the right time, often years or even decades after launch, which is exactly why this next detail really matters. Mercury's orbit has got a slow twist in it. Its point of closest approach to the Sun, called the perihelion, shifts around over time. If you account for the gravitational nudges from the other planets, Newton explains almost all of it, but not quite. There's a tiny leftover, just 0.012 degrees per century, sitting there like an annoying grain of sand in an otherwise perfect machine. And that annoying grain of sand shows that Newton's model, despite being brilliant, isn't quite right. And let's face it, when a model can get you to the moon and back, a slight mismatch isn't close enough. It's a clue that you're onto something. And this is the point where we meet one of the great minds of 20th century physics, Albert Einstein, who has the annoying habit, which is shared by very few people in history, of turning up and making a problem disappear by changing what the problem actually is. By the early 1900s, Newton's machinery was running beautifully. You could predict the positions of the planets, you could build bridges, you could fire cannons, all that good stuff. But then there was Mercury, that small, annoying twist in its orbit that just wouldn't go away. Einstein published his theory of general relativity in 1915, and in it he kept all of the bits of Newton where gravity is weak and speeds are slow, which are the things that we're used to in everyday life, but he completely changed our view of what gravity actually is. In Newton's model, you see, gravity is this force that pulls objects together from across space. But in Einstein's, gravity is what you get when mass and energy warp the geometry of space-time, which sounds like philosophy until you realise that it actually produces numbers. If you put a planet close to the Sun, such as Mercury, where space-time curvature is strongest, the orbit isn't perfectly elliptical anymore. It's an almost ellipse, but it doesn't quite close. As it rotates, the perihelion advances slightly. And when you run the numbers, general relativity makes up the exact bit of leftover that Newton just couldn't explain, that annoying 0.012 degrees per century. And so general relativity really picks up where Newton left off. It explains everything that came before, the positions of the planets in the sky, the ellipses, Newton's laws, all of that, but it just irons out the wrinkles that Newton couldn't quite manage. And it's not like general relativity is some specialist tool that we keep in a drawer labelled Mercury. A clue's in the name. It's general. It's our best working description of gravity itself, which is quite saying something because gravity runs the universe's large-scale architecture. So that's the story, and it was the point that I was trying to smuggle into that dinner party at risk of starting a riot. Science doesn't hand us truths, it hands us models. The best explanation we can make from the evidence we have written in plain language and mathematics. And those models survive for however long they keep on matching the world, and then eventually they get revised or replaced entirely when we have better observations. Ptolemy's geocentrism wasn't useless. It was a working machine that did actually explain a lot, until the complexity started to make it creak. Copernicus simplified things, but his insistence on circles limited the accuracy. And then Tycho came along and raised the standards of measurement so high that hand-waving stopped being an option. Kepler let those measurements force the shape, ellipses with the sun at one of the foci. Newton explained why the laws work and built a model of gravity so powerful that we used it to land humans on the moon and bring them home safely. And Einstein kept all of it and explained the leftover, because gravity, it turned out, is just space-time geometry. It's the best model we have for gravity across the universe. But even general relativity, as good as it is, isn't the final answer. It can't yet be stitched neatly with quantum physics, for example, which is exactly the point. Even our best models, even those produced by Einstein and Newton, are only provisional. And so with all of that, the most scientific sentence that you can ever say is also the most honest. That's just our best explanation so far.